Hey guys, what's going on there? In this video, we're going to be looking at hyperparameter tuning for in machine learning. All right. So this is one of these videos that is going to kind of unravel some insights on what hyperparameter means, and then we're also going to perform a practical using a real-time data set. All right. So if you actually join, this is machine learning for everybody. So it means that basically everything we're going to be explaining here, it's meant for anybody who is interested in getting their hands dirty and machine learning. So without wasting much of our time, right now, what I'm going to be doing now is I'm going to be importing our data sets. We have it there, and we're going to be coding in with VS Code. I'm going to set my environment up before I basically plunge into the training. Okay. And I'm just going to click on this and I'm going to say this is practice. Okay. So you can create a folder and I'm going to select that folder and automatically it's going to take me out from here. Now, basically what I'm going to do now is I'm currently here. I'm just going to close this. Then I'm going to close this to our practice.interactive Python notebook. Okay. And I'm going to come and select my kernel and I'm going to let that dictate. Now, so we're going to jump straight into what we have today. So, like I said, we're going to be talking about hyperparameter tuning. Even if you don't understand what hyperparameter tuning means, before we finish this particular session, I believe definitely is something that is going to be easy to understand. And of course, we're going to get hands-on with what these terminologies mean. Now, imagine you're trying to train a machine learning model, and for example, if we're looking at neural networks, we are usually more concerned about their weights, right? Because the weights that some of these input variables have in neural networks plays a lot of role in how the model makes prediction. Now, we want to actually look at this hyperparameter tuning as you're trying to conduct a training in a university, right? Let me just use that as an example. And now there are actually some metrics that is going to determine the quality of that training. Probably the number of teachers the university has, if the university has a vice chancellor, or if they have, so and so laboratory, the conditions of the laboratory and all that. So these are what we call kind of parameters, right? That's going to determine how well training is going to occur in that university, like the outcome of the training. So that is something that happens in machine learning, where there are some kind of I'm going to put it as there's some criteria that our algorithm is going to use in tuning the model. Maybe probably how deep is it going to go, how many search, how many epochs, some of these parameters is going to determine how well we can get the best estimates in our model. Because if you come to a university that has 100 lecturers and another university that has two lecturers, maybe 10,000 students, and another one has 100 lecturers and 10,000 students, essentially, both of them are not going to perform the same way because one has more higher, parameters compared to the other one. That is just the idea that I wanted to have. So hyperparameter tuning is kind of how do we optimize our some of the parameters that we have in our model to get the best possible outcome. That is just what hyperparameter tuning is. So it means that we're going to pass our model through various estimates for you to be able to get the very best parameter that is going to be important for us. That is what hyperparameter tuning is all about. I might really want to kind of read so much of theories here, but I just wanted to kind of have a very, very rudimentary understanding of what it talks about. And then that way you can actually plunge it into anything you want to do. So hyperparameter tuning is kind of the process of finding the best values for this kind of settings, like maybe I talk about weights in a neural network, how they are trained automatically from your data, and then, unlike in other settings, like how the complex model should be or how fast it learns, and it's something that must be set by you before the training begins. And we also asked you to think about it like, when you're calibrating a medical device, you kind of set the dials before the test begins, and the right configuration determines, the quality of the result. So hyperparameters are not learned during the training. It's something you're going to choose. I'm definitely going to illustrate that in practicals so that it's going to make a lot of sense. And your choice has, a major impact on the model accuracy. Now, we're going to actually be distinguishing between parameters and hyperparameters. Now, these are actually two terms that a lot of people, beginners particularly, usually confuse in machine learning. And this is kind of a breakdown of what uh, some of these parameters, some of what these ideas are. Now, when we talk about parameters, we're trying to say, okay, you need to learn from data during training, right? So you don't set these rules manually in the algorithm. So when we talk about algorithm and models, we're talking about random forest classifier, decision tree classifier, support vector machine, gradient booster, logistic regression, linear regressor, and a wide array of them. So what we're saying is that some of the weights, the coefficients that come inside of that, the vectors in support vector machines, you don't set those ones manually. It is what the algorithm figures out on its own. But for hyperparameters, you are the one that sets it before the training starts. So this could be like how many number of trees do you want the random forest to have? Learning rates in gradient boosting. Do you want it to be? What do you want it to be? The probability is also true. Regularization of strength, C in logistic regression. So these are parameters that we choose, like gamma, kernel, for support vector machine, and the wide array of them. So I'm going to tell you how we can actually understand these parameters and make their choices, particularly in the practicals that we are going to lay out right now. So for example, now parameters are like your muscles that adapt to its exercises, whereas hyperparameters is the workout plan you design before training begins. Do you understand? So the parameter, your muscles now, how they are going to be coming out is just basically the parameters. But then the hyperparameters now is now like the workout plan you design before training begins. Now, but the question now is, why do we perform hyperparameter tuning, right? Why are we really interested in hyperparameter tuning? And the reason why it matters is because if we actually skip tuning, skipping this tuning is one of the most common reasons most machine learning models underperform. And the default settings built into scikit-learn are reasonable starting points, but they are rarely optimal for specific data sets. So what I'm trying to say here now is that when you go to your training data here, and maybe, for example, you see something like, let me just give an example, maybe from sklearn dot maybe 3. Okay, I'm trying to select my kernel, so that's going to run. So let's say, for example, see from sklearn dot 3 import decision tree classifier, and we'll say model, for example, we say model is equals to decision tree classifier, and then we'll say model dot get params. Now, basically, what this is going to do, model, so what this is going to do right now is that it's going to kind of return some parameters that we can actually insert. And these are what we call default parameters in scikit-learn. So this is where we imported this from. So these are some of the default parameters, although they are somehow kind of okay to get started with, because if I just kind of maybe go here and say model dot fit, maybe x string scaled, x, and all of that. The truth is that at the end of the day, what is going to happen is that I might get my accuracy, but I should still do what we call hyperparameter tuning to see if I can get the very, very, very best estimates. This is what we are going to show in practicals right now. But what I'm trying to talk about right now is that these are kind of default parameters that scikit-learn assigns for decision tree classifier as an algorithm, okay? So those are the parameters there. So they're actually good starting point, just like I said, right? They are very good starting point, and but they are kind of really optimal for your specific data set. So there are some kind of certain type of data sets that you might have, then it might actually require some, or maybe some other kind of detailed parameters, right? So the reason for hyperparameter tuning is that it's going to improve the accuracy, because by the time we now check out some of those hyperparameters, then choose out the best estimators. And we cannot get we also get the best estimator. Of course, that means improved accuracy. Our model performs better because the right hyperparameters can drastically boost your model's predictive performance on real data. Now, another thing there is that it kind of prevents overfitting, right? Hyperparameters is going to prevent overfitting because tuning keeps your model from memorizing training data and failing on new unseen data. And again, is that what? It makes our model much more reliable, because a well-tuned model generalizes better, critically, when the stakes are high, like predicting diseases. Now, what is a simple starting model, for logistic regression? Now, before we tune anything, we need to actually introduce the model we'll use throughout this tutorial. For example, logistic regression is simple, interpretable, algorithm, great for binary classification, tasks like predicting whether a patient has a disease or not, and all of that. But we kind of need to understand that, there are actually some params that we will get to understand. Because here now you can actually see this basic setup here where we go to scikit-learn, we import logistic regression. We go to scikit-learn the data set, we import the load breast cancer data set. We have other data sets as well. Then we import trait test split. Then we see data is equals to load breast, whatever, breast cancer data set. Then we X-train X test, Y-train Y test, train test split, data target, and then we have our, what do you call it, our test size, and we can actually decide to return this as XY. That's still going to work. And we kind of call our model, then we fit in X-ray, and then we get our score. So what this thing is doing now is that we are loading the breast cancer data set in a classic healthcare classification problem with 30 feature population. Then we split it, and then we train on a different logistic regression model and evaluate it. Now, this is kind of our baseline throughout this tutorial, because we're going to tune this model to see how much better we can make of it. Now, what I can actually do now is I can actually decide to add this on the scikit-learn tutorial, so that you can actually get some, maybe I can decide to kind of copy this and put it in our data sheet. But then I think I would still like us to work on a fresh data ourselves. So some of the common hyperparameters to know, because different algorithms have different hyperparameters. So what we mean by that is that if you come here and you go to, let's say, for example, from sklearn, dot maybe ensemble, and you import the gradient booster classifier, and you see model is equals to gradient booster classifier, and you see model dot get params. Of course, it's going to give you some parameters for this gradient booster classifier. And you see that somehow this is slightly different from the decision tree classifier. Okay, you see this one ended with splitter, this one ended with warm start, this one had verbose, this one doesn't have that. You see that these are what different what params. That's what we mean by that. Okay. And but a few show up again and again across most models, and these are the ones that they are the key ones that give you a strong foundation for tuning any model, like regularization strength, number of trees, learning rate, max depth. Okay, so what learning rate regularization strength does is that mostly in linear logistic regression and support vector meshing, kind of controls how the model is penalized for complexity. A low C is equals to simpler model, and a high C is what? More complex and may overfit. So for this number of trees, is usually used in ensemble methods like random forest, where more trees, generally means better performance, but then slower what? Training. There's actually a point of diminishing returns. And then also what we call learning rates. And for learning rate, here we're saying that it's used in graduate booster models to control how fast the model updates. And if it is too high, more like it misses the optimal solution. And if it's too low, then it takes forever to converge. Then we also have what we call the max depth, right? Which is used in decision trees, and it limits how deep the tree can grow. The deeper is the more complex, the shallower, the simpler, the more generalizable. So kind of look at the logistic regression model here. We could just say from sklearn dot linear model, import the logistic regression. Okay, we're going to say model is equals to logistic regression. Let's say model dot get params. Now, one of the things we're going to see here for this particular model, logistic regression, is that you see it has penalty, random state solver, verbose, maximum iteration, and all of that. And one of the things is that if you look at our slide here, you see that what? It has some of the, so it has some of the parameters that we need to use to take into account of what we are doing. So the next one we're going to look at right now is we might now want to talk about some other parameters. So I want to now look at overfitting and underfitting. And this is something we've talked about severally in our previous session, where we said that bad tuning creates one of those problems, one of two problems, and understanding them is kind of very important. Underfitting is whenever the model is too simple, it has a high bias, and of course, it misses some kind of patterns, and then it's low training and test accuracy. Whereas for good fit, it's where it is now it's balanced, biased, and then and variance, and then the model basically performs well on both data sets. And then again, what we call overfitting, which is usually identified to be that the model is too complex and it has some kind of high variance and it memorizes the data training, and again is that it kind of has a low test accuracy, because when you now train it on real world data, you find out that the accuracy is quite very poor. Now, under fitting, the model is too simple to capture the patterns in the data. That's why it's increasing model complexity, okay? So the more higher max depth, lower C or reducing the organization can help. And for overfitting, the model memorizes, training data but fails on new data, just like I talked about a couple of minutes now. And, adding regularization, limited tree depth, or using cross-validation helps to prevent this very well. So this is just basically some of the hyperparameters that we talked about in our previous slide. Now, manual tuning is also something that holds water, because the most basic approach to hyperparameter tuning is to manually try different values, and see what works best. And it's something that is very tedious and not systematic, but it builds some kind of crucial intuition for what hyperparameter means. So if for example, here now, we can try different values of C, and let's say we see logistic regression C of this, model.fit, all of that. And then we can try C1 at default. We can try C100 also, and a lot of them. So one of the reasons we are doing is I want to kind of get the best parameter, and each value of C changes how much the model is regularized. And it is similar, to like what I'm trying to talk about right now is larger values definitely is going to allow you to fit in through the training data more closely, while manual tuning works for 1 to 2 parameters, okay, hyperparameters here. So it quickly becomes impractical when you have many settings to explore. That's where automated search comes in, what we call grid search. So don't ever tune your testing data set. It's very, very important. And always evaluate your tuning choices on a validation set, or use cross validation. So we have what we call grid search, and this is kind of a method that we use to try several combinations. So grid search is one of the most thorough hyperparameter tuning method. You define a grid of values for each parameter, and the algorithm tries, every single combination, evaluating each one, using cross-validation. So what we start by doing is that we define the parameter grid, and then we specify the hyperparameters to tune and what values to try for each. And then we perform GridSearchCV, which trains, and evaluates. And then what GridSearchCV does is that it kind of trains and evaluates, for every combination, and it fits the model and scores, using k-folds plus validation. So that is where we are definitely going to select the best parameters, and then the kind of combination that produces the highest average cross validation, score, it's returned as the winner. And that's what we're going to be showing in practicals. So what GridSearchCV does is that it guarantees us the best, combination within our defined grid. And but it can also show you when the grid is large. So guys, this is just kind of an example of what the grid search it looks like, and we have some. I could just show you that. Okay. So this is just kind of an example. Okay. This is just basically an example. We're going to also have a practical here, live and direct. So what it does is that, first of all, is that it fits this thing into five-fold, combinations of the kind of 50 models total. And then it breaks it down. CV is equals to 5. That's the cross-validation split. And then it splits it into five-fold. It tries to understand the scoring accuracy. That's a metric used to compare combination. And then the params, it tries to get uh, define the grid of values to search. And the grid search series runs all 10 combination, 5 values of C times 2 solvers, each evaluated 5 times. That's 50 models, that fits total. So for a small data set like breast cancer, this is very fast because in healthcare, scoring is equals to ROC or F1 and is often used, better than imbalanced, better than accuracy for imbalanced data sets. So this is just what it means like, once the research is completed, scikit-learn is going to give you access to, the winning configuration of how it's performed. Here's how to extract and use some of those results. So you can actually go to best params, grid best score, grid score, and of course, yeah. So the result, what the results actually means is that when you go for best grid.best params, it tells you exactly which combination won the search. In this case, it could be C10, an LBFGS solver, and then also for best score, which is another important parameter that we always look out for. It is kind of the average cross-validation accuracy of all five folds, and it's kind of a more trustworthy number than a single, maybe train test plate and all of that. So the best estimator is also another information that we will get from the grid, which it is the tuned model that improves on the baseline. So in disease prediction, every 1 to 2% accuracy gain means a hundreds of correct diagnosis. So this is also an illustration of, grid search. We can also perform random search, and instead of grid, random search is kind of a faster alternative to get hyperparameters because grid search is thorough, but it's very slow. And when you have many hyperparameters or large ranges, random search is the best. So random search samples a fixed number of random combinations instead of trying all of them. And then it kind of often finds the near optimal results, in a fraction of time. So some of the key advantage here is that with this search, you must specify the exact values to try. But then with random search, you can define a continuous probability distribution with uniform and sample from it randomly. So this is something that's going to let you explore a much larger space without the computational cost. And N eta means only 20 combinations are tested. Compare that to 100 or 1,000 with full grade. Because we are sure that research shows that random search often finds some kind of maybe just it finds a random search is something that finds a result just as good as GridSearchCV. So that is quite very important to understand, and it's the good choice for large search processes. Now, so this is just a visual illustration between grid search and random search because both of them are widely used in practice, and choosing the right one depends on your data search. And probably whenever you have a very large data set and all of that, you might want to go for random search. And if you have something that is smaller, maybe you might go for grid search. But then, this one is exhaustive. This is sampled. This is fast. This is slow. This is small grid, and this is large space, and this is best in grid, and this is near in optimal. Now, another thing I want you to understand is that you need to use random search whenever you have four hyperparameters and the ranges are large or continuous. You need the results quickly. And for grid, you need to use it whenever you have 1 to 3 hyperparameters and the grid is small and well defined. All right, so these are done now because we're trying to move that. And then cross validation is also another thing that is important to understand because it's a very, very secret ingredient that makes hyperparameter tuning very trustworthy. And without it, we risk tuning our model to a lucky train test split rather than a true underlying pattern. So what we do is that we split into key folds, we train and evaluate, we average the scores. And whenever you pass CV equals to 5 in GridSearchCV, it automatically performs some kind of 5 folds cross validation. And then again, for every combination, it tests. This means that each configuration is evaluated on 5 different subjects of your data, and the average score is used for computing or maybe probably comparison right there. So yeah, of course, it's definitely going to give us a kind of much more reliable estimate. So we can tune decision trees as well. Decision trees are highly intuitive that split data based on thresholds and but without constraints, they can grow extremely deep and overfit your training data. So I want to just make it clear that the most important hyperparameters to tune for decision tree is high max depth. And there are also there are also other parameters like mean samples, criterion, and all of that. So we could just see how it looks like. So the reason for max depth there is because it limits how many layers that are of split, and then none means unlikely, kind of risky. For higher simple tree, so this is that's for more of for mean samples split, the minimum samples needed to split a node, which is higher is equals to simpler tree. So criterion is that the formula used to check the best split is now the same also applies for k-nearest neighbors here. I guess in our practical shortly now, we might want to use at least 1 or 2 or more models to perform some kind of example. So for k-nearest neighbors, it tries to look for the k-nearest neighbors, that's the nearest neighbors in the training data and takes inputs. So the choice of K is critical, it's too small, and the model is noisy. So if it's too large, it becomes too generalized. So for sklen.neighbors, import k nearest neighbors classifier. Then from sklearn.model selection, import GridSearchCV. These are the parameters that we need. For metrics, you can look at the Euclidean, Manhattan, for weights, uniform distance. Somebody might be asking, then how do I get this? You can always get all this information from the documentation. Okay? And then you pass your GridSearchCV and all of that, grid.fit and all of that. You try to get what you want. And if you put your key hyperparameters here, you can, to explanation, you might want to say that for n neighbors, it's all about how many neighbors voted, odd numbers avoid ties, and then weight is equals to uniform, it's trying to get the kind of uniform where all neighbors are equally voting, and then the distance kind of is, there is kind of a closer neighbors count more than distance. And then for metrics, we're trying to know how distance is being measured between what the patient. Is he using the Euclidean distance or the Manhattan? So we can actually evaluate our tuned model as well. It's done where we can, when we get our best params and our best estimator, we can now perform some kind of prediction, get our Y prober and our Y pred, and then we can run our recall, which is sensitivity. We can run precision. We can also run area under curve reciprocal pattern characteristics. So this is just to make you understand that in this video, we might still run some predictions using our data set. So there are lots of real-world examples out there, and this is how hyperparameter tuning directly improves outcomes in healthcare setting. Let's say we're using breast cancer data to classify tumors between benign or malignant. The baseline accuracy could be 95.6. That's the default logistic rating without tuning. And after we tune it, it could move from 0.6 to 0.4 of 97. And then the area under curve is now 0.9991. And extra correct diagnosis is less than 10. So that's just kind of an intuition of what it looks like. So some of the mistakes I would want you to avoid during your tuning, and as also how we're going to show some practicals, is that even the experienced practitioners fall into these traps, and then knowing them in advance will save you hours of debugging, right? And protect the integrity of your model. So if you're tuning on the data set, if you use test data during tuning, your model is going to secretly peck at the answers. Your report accuracy will be very optimistic, and it won't be very suitable to reflect on real life data. Okay, and that's kind of the accuracy when you put a real life data. And that's why it's always important for you to use a validation set or cross validation. So if you're tuning too many parameters at once, it means that exponentially more combinations. So just start by tuning 1 to 2 hyperparameters, and then that matters really very well, and then refine from there. Adding 5+ parameters to a grid search can make it run for hours. So another thing is, if you're ignoring cross-validation, that's another common mistake people do, because a single train test split can be lucky or unlucky. So always use cross-validation or higher in your search to get a stable, trustworthy performance estimate. And again, using accuracy for imbalanced data, if 95% of patients are healthy, then a model that always predicts healthy gets maybe 95% accuracy, but it's useless. Again, we need to use F1 recall or your AOC, ROC for that. So there are lots of metrics that we need to use when we are tuning for our parameters. So what's actually the summary we can get from it before we jump into the practical here is that your hyperparameter tuning workflow, you now have some kind of complete uh, practical toolkit for tuning machine learning models. And the full workflow distilled into an actionable sequence you can apply to any classification problem. First of all, you need to define the grid. You create a parameter grid with meaningful ranges. You run the search, you use GridSearchCV or randomized search CV, you see if it was the file, you choose the model, you kind of select the logistic regression, the decision tree or k-nearest level baseline, and then you evaluate the results with that. So thank you very much for actually staying to this time. The next one we're going to be doing right now is we're going to be jumping straight into the coding and using a real world time data set. Okay. So that is actually what we're going to be performing right now. And to make everything very simple, we're going to go from downloading a data set that we got from Kaggle. And that's actually a data set that reflects around diabetes. And that's exactly what we're going to be using for this particular exercise to get all of what we've talked about now into that's just to basically download all the insights that we have and have a much more clearer flow on what we're talking about. So I'm just going to jump into VS Code, and of course I could just come up, and this is where I'm going to be running some of my code. So remember, as usual, the first thing you might want to do is control backtick. You have to install your dependencies for this particular exercise because it's quite very imperative for you to install those dependencies. And then when you've got those dependencies installed, excuse me, you might not want to now start importing the necessary libraries. I'm going to import pandas as PD. I'm going to import NumPy as NP. I'm going to import matplotlib.pyplot as PLT from sklearn. I'm just kind of going to share this. So from sklearn dot, so what are we going to be doing? Dot pre-processing. I'm going to import standard scalar. So from sklearn dot model selection, so I'm going to import train tail split. So we're going to also import GridSearchCV because we're going to be using it. So we can also import random search CV. All right, but we're going to be working with the GridSearchCV for hyperparameter tuning. Now, the next thing we're going to be importing now is from sklearn. Now, we're going to be using the logistic. So we're going to get that from the linear model, import logistic regression model. Now, from sklearn dot metrics, we're going to import accuracy score, precision score, F1 score, recall, classification report, and also we're going to import ROC, AUC, and ROC curve. I believe we have all the dependencies imported. If there is anything we might want to import, later on, probably we're definitely going to return here. So we're going to run that. Now, what I'm going to do now is I wanted to use an object-oriented approach, programming approach, but I'm not going to be doing that. So that's what we're going to be working with. So we're kind of just going to keep this very simple. And the first one we're going to do is df is equals to pd dot read CSV. And then we're going to pass in the name of file, which is data.cv. And we could say df.head. We'll say df.head. Of course, it's going to give us this. This is what our data set looks like. So we'll say df.describe. So it's going to come and give us a numeric summary, data summarization of numeric values. And so we're going to do df.info. To get all the information about the data set. We have lung cancer, which is what we're going to be predicting, all right? So this is going to be a lung cancer prediction. Yeah, so we have its object here, we have gender here also. So, of course, machine learning works with numbers and all of that. So the next thing we're going to do right now is since we have this df, we'll say df dot is duplicate. So I want to know if dot sum. Okay, so there are duplicates here. So basically that is what we are doing here to check duplicates. Now, but then let us understand what df dot shape means. So it contains 3,000 rows and 16 columns, okay? I could just bring this up a bit slightly so that we can see my screen. Now, the next thing I'm going to do now is I'm going to say df dot endtime. That's what is going to return. It's going to return to, so it means that our data set, our data set is in 2 dimensions. Now, we're not really going to waste so much time. I'll say df dot columns dot to list. Cannot take it to list. So this is what our data set columns looks like. So we can say for df columns is going to be equals to df dot columns, and we want to kind of handle these columns properly. Dot as type string. Okay. String dot lower dot string dot strip, and I think that is open, so that should work fine. So if we check our column df dot columns, it has now been normalized, okay? Now, we could remove duplicates. So df is equals to df dot drop duplicates. And then to confirm if so I'm going to say df dot we're going to say df dot shape. So you can actually remember then it was 3,000 by this, and then we literally found out that we have so you can actually see we found out that it is we have 3,000 3,000 rows and 16 columns. All right, so we are moving, and the next thing we are going to do is okay, trying to just to be sure that our whole thing is running. I'm just gonna refresh this. Okay, so the next thing we're going to do right now is all right, so what we're gonna do now is that after we've removed columns, I was trying to just kind of position my screen. Um, so we're gonna load that again. So we're gonna kind of let it load. All right, so what we can do now is so a cool rundown. So I think I have authored with a setting. I'm trying to ensure. I'm trying to kind of install everything. Okay, so just a second. We're trying to get set. Okay, I'm trying to get those params. My keyboard seems to be kind of misbehaving. So what we might do here now is that we might use the Jupyter notebook, and that is what I'm going to be doing right now. So, yep. Okay, so yeah, that works very fine. And okay, so what we might do, we kind of switch to Jupyter Notebook so that we can basically perform that intensive practical. So I'm just going to come click here and I'm going to search collab. So we're going to open the Google Colab. All right, so I'm going to kind of create a new file and so just to demonstrate what I'm talking about, okay, or basically, I think we could just do what we want here. We do some kind of TensorFlow practice, and they were quite very useful. So what we're going to do right now is we're going to kind of drag our data set. I'm going to bring that here. I'm going to drag this. So we'll let it load. So it's loading. I'll let that load and all right. So I think we're going to rule around this. We're going to use continue with this. Trying to get everything set up back so that we can continue firing. Apologies for the kind of delay. Okay, so we're going to run all, and of course, this is going to clear. It's kind of connecting to the kernel to just give you some time. Trying to. All right, so if we do df dot shape, it's gonna give us this, so we are good to go, guys. And now the next thing we might want to do now is we have our we have actually removed the duplicate, right? So what we normalize this. So for gender, let's kind of see what's inside of there, the unique. Okay. So what this means now is we kind of want to convert it from from an object type to an int, right? To kind of numbers. Because computers doesn't really remember numbers. Remember when we did something like df dot d types, And it kind of showed us a list, where we have gender as an object, age as an int, smoking, yellow fingers, and all of that, and a lot of them. Okay. So we're going to convert for gender and also do the same thing for, I'm going to say df of lung cancer dot unique. Okay, so it's going to tell us yes or no. So we're going to convert all of this into numbers, what we call encoding, right? So I'm just kind of going to put a mark down there. I'm going to call this encoding. So guys, what I'm going to do next now is, so the next thing I'm going to do right now is I'm going to now say for df of gender is going to be equals to df of, I think I could still copy that again, dot map, then I'm going to pass a dictionary, and then I'm going to have male as 0 or maybe 1, and then f as 0. So we're also going to do the same thing for, so I think I'm just going to run that so that if I show you df of df dot gender, you're going to see that it has an array that contains zeros and one and all of that. We're going to see the value counts, and of course it's going to be, you have 1,500 men and 0 and 486 female. Now what we'll do next now is we could say df of lung cancer is good. Of course I'm going to copy that. Then we go to this dot map, and I think we should have actually checked if there are null values, and of course there are not. That's is what we call non-values. Okay, and I can also check df dot is null dot sum. Sorry, to take out that. Okay, so create doesn't have any attribute dot sum, and of course that this is what it's got, and then what we probably has removed some duplicate, and I'm going to come back here, and then for lung cancer, we have no and yes. So I'm going to say no, 0, yes is going to be 1. I think this should be in a dictionary. So of course that's going to work out, and then we're going to now say df does, this is going to be equal to pd dot to numeric, and then we'll still pass that. And errors is equal to course, and I want to say dot as type int. Okay, that's taking some time. automatically it's already converted to numbers. So we have those noun values there. So, but if you want to actually get the distribution of lung cancer, let's say we just do something like plot.hist, and then we have maybe df dot lung cancer dot values and df dot last value counts. Scores is equals to this, which and the values, I think this is going to be bar and scores dot maybe probably this should be index. Are they label here? I don't think so. We say the color is equals to the player, and I'm going to say plot dot x label. That's going to be maybe CS is going to be 0, 1, and it's 0. And then say alpha 0.7. Then we'll put our plots.title, and then we have maybe we could call it distribution of maybe what are we going to call this? I'm going to say lung cancer or not. Distribution, and then we can now say plots that y label. I'm going to say it starts the count and label show, and the that's read true. 0.4, and I think that should work. Okay, so what's the issue there? Okay, guys, so what we want to do right now is I don't just really want to keep this so much on some maybe let me just kind of copy this out here and show what I'm trying to talk about. Okay, so scores dot index. Okay, that's going to give me a float. Is it in code? No, it's not callable. It's not. It's what is cause, and Okay, we need to restart all this kernel. We need to restart it and run it again. Beautiful, beautiful. So you could see how we worked on this basically. And you can actually see our visualization right now. We have a lung cancer and all of that. So we could decide to trim this to a wide lane and have it count here from here. But this is just kind of a matplotlib visualization where we have this now here as 0. And then I think I could just add something like plot dot maybe x lim at 0 and 1, and then plot dot y lim at 0. No, I'm not going to add anything for y lim because so that's going to work really very fine. Yeah, so this is just what it looks like. The So I think the X ticks, can remove the X ticks. So it's a plot dot X ticks, let's say none, but you're not gonna say none. That's like you need to actually like pass something inside of there. But I am not really teaching matplotlib right now. I just want to kind of have a visualization right there. So guys, so that is that for our lung cancer. That's that particular part of the column. And then we can actually do df dot d types, to be sure that everything is an int. And of course, we can now perform we can now assign, right? We can basically assign our value. So we can say df dot columns dot to list, and then it's going to give us this list. So I could just copy that. Then I'm going to now assign other X is going to be, so I'm going to say features here, because we have what we call features and targets. It's going to be this, and then I'm not going to make it two-dimensional on this. So just take out the lung cancer there, and that's our features. Then since our X is equals to df of features, and our Y is going to be equals to df of lung cancer. So that works really well. No issues. Now, so we're going to actually perform some kind of scaling here. So what do I mean by scaling? So what I mean by scaling here is after we have splitted our data, we can now perform some scaling. And that is where we can now do something like X train, X test, Y train, Y test is equals to train test split X, Y. Then we have our test size of 0.3, and then a random state of 44. So I'm going to run that. And so I'm going to run that. So the next thing I'm going to do now is, now I'm going to kind of scale this. So I'm going to, sorry, not that. I'm going to kind of scale this. I'm going to say scalar is equals to standard scalar. And I'm going to say x train scaled is going to equals to scalar dot fit dot transform x train one x test scaled is equals to scalar dot transform is transform now x test. So that should, okay, I made a mistake. I put this there. So this is what is going to be, right? And then I'm going to now, so we are good, right? So this is what we're going to work on, our x scaled and our x train scaled. That's our x train scaled and x test scaled. So what I'm going to do now is, because we're going to perform hyperparameter tuning, is I want to really get the best estimate. But with this now, we can actually perform our prediction. Because if we do x train scale dot maybe shape, you see that we have 2098 then 15 columns. And then if we do the same thing for, let's say for example, we'll do for y train dot shape, you see we have 2098 column rows. So we're going to actually do our model training, and that's what I'm going to do. So what I'm going to do right now is, now this is how hyperparameter tuning comes into place right now. So we could just say model is equals to logistic regression model. You might want to put maximum iteration at 1000, which is usually what we do before. That's kind of what we call manual hyperparameter tuning, right? But now I'm not going to say model.fit x train scaled and then y train, and then we're gonna run that, of course. So it's going to kind of show us all of these parameters, our model is running, and we can just do something like we need to perform some kind of prediction. Let's see what it's going to be. So we can actually say y-pred is equals to model dot predict, then pass x test scaled. And then of course we can run that. And if we actually print y-pred, it's going to give us an array of zeros and one. That's a lot. Now the next thing we might do now is that since we've already performed that, we can now get our y-prober. Our y-prober is going to be x, no, it's going to be model.predict prober, then we'll pass x test scaled, and that's going to be the last column. So that's fine. So we can perform we can print, we can get our metrics, okay? Now this is getting our metrics before we perform hyperparameter tuning so we can compare, right? So our metrics. So we're going to get our metrics. So some of these metrics here could be, so I'm going to call these metrics before hyperparameter tuning. So for accuracy, we could have something like print accuracy, and the accuracy is definitely going to be accuracy score plus our Y test, Y pred. So this is something I'm going to do for accuracy. No, we've done that for accuracy. We're going to do for precision. We're going to do for F1 score. We're going to do for what else? F1 score, well, classification report, recall. So I'm just gonna put that there. And then we're also going to have our recall. Recall score, which is this, and then the same thing will apply to confusion matrix. I don't know if I imported that from sklearn.metrics. Import confusion. Somewhere like confusion matrix. So we can print this, and of course we have all our metrics. I'm kind of going to add a new line here. So this is what it is. We have an accuracy of 60%. Now we have an accuracy of 50, despite scaling. Let me change this to min-max scalar. And yeah, so let me just import the min-max scalar. And then let's see what happens. That's our scalar. I'm going to change it to the min-max scalar. So run on. Let's see what happens if it's okay. Still 50.3. But then maybe when we perform hyperparameter tuning, we will know. So the next thing we're going to do right now is I'm going to import from sklearn.model selection. I'm going to import stratified k-fold. So what we use this to do is to split our model into short form, and I'm also going to import cross file score. So I'm going to cross validate. And then for for some kind of, to get multiple parameters. Now, I didn't print out a matrix for ROC, so I'm going to say my ROC score is going to be equals to ROC AUC, then when you have your Y test and your, your Y rubber. I want to be sure that was printed. Y program. Trying to make sure that everything runs. Okay, this is Excel skilled. Oh, sorry. Excel test. So that works fine. And just to be sure everything runs through. Okay, so that is Y proper. And we can actually, if we print this is going to give us ROC score. Okay, so this is what it is, 50. So what we'll do now is we're going to plot our RC curve. So we're going to say FPR, TPR, then we have underscore threshold is going to be equals to RC curve, then we'll pass our Y, our score, right? We'll pass our Y test and our Y proper. And then so this is going to be the last visualization that we're going to be performing. Plot the plot. Then our FPR, TPR label is going to be equals to RC EUC. Then we'll have our RC score. And we can decide to pass RC AUC score. This is going to be a RC score and 01. For long answer. There was a plot dot. Here's a plot dot Y label. I'm going to call that true positive rate because basically I was just trying to find the distance there. And then I'm going to say plot dots. What else are we interested in? It's a plot dots X lim. So that's going to be 0, 1, plot dots Y lim is going to be 0, 1. Let's say plot dots legend. Plot dots grid. and that's going to be true, and then say alpha is equals to 0.6, and then plot dot show. That should work. I want to know why this score didn't show. Okay, we didn't add an F string there, that's why. Of course, that's going to show now. And I kind of think can be 2.2f. So that's rounded up. You see that this model, this particular model performs really very badly. And now, so that is that, right? This is ROC before hyperparameter tuning. Now, what is now hyperparameter tuning? I'm going to be performing what? Hyperparameter tuning, okay? So we've done a lot now, but yeah, we're yet to perform the hyperparameter tuning, and that's what we're going to be doing right now. So to get that on, what we will be doing is now, first of all, we're going to call our model is going to be equals to logic. We're going to say, I'm going to call this hyper model. It's going to be logistic regression. So it's not going to take in any parameter. So we're going to have a param grid is going to be equals to a dictionary. Now, if you remember, there are some certain things we need to take in our C, or maybe our C, because if we come to logistic regression, say model dot get params, if we call this function, it's going to give us that we have C, and we're interested in some of these. Solver, I'm doing solver penalty. And so I'm just going to, and that's a dictionary. So all can do could just paste that here. And jobs as none. Of course, this is going to be at the bottom of my dictionary. And for solver, it's going to be in a list. Then I have for C, and I'm just going to kind of paste that in. So that's where I got it. And it's going to be in a list as well. So we can have something like maybe 10.0 and all of that. Penalty 2, I could just put it in a list. Maybe I could put 20 and all of that. But I wonder why that's in extra. It's um, basically other things. So this is just where I've kind of outlined some hyperparameter tunes for logistic regression, where we have for solver, we have labeling and all of that. So I could just take these parameters and yeah, put it there. So this is just basically what it is. And what is the issue? So this is param grid. So that is what it is basically. And remember, we wanted to perform some kind of cross value. I'm just going to run that so that is going to run without an issue. But when we finished here, let's just perform some kind of cross validation of our methods. Then we can now use some of that in our hyperparameter tuning. So first of all, we have scoring values. So what are the parameters that we're interested in? We're interested in accuracy. We're accuracy is going to be accuracy. Precision is going to be precision. Recall is going to be recall. F1 is going to be F1. And then RCAC is going to be RCAC. Then CV is equals to S35 keyfold of N splits at 5, and then shuffle is true, random state of that is true. Now what we can do now, we could see log results is equals to cross-validate, then we pass in our model X scaled. Okay, I think this is just X and Y. We are not really passing in what we've scaled. And then, yeah, because we can't pass that in now. And then we have our CV is equals to CV. Scoring is equals to scoring. So there should be a random state or something. Okay, right, so let's print some of those cross-validated scores. So if we want to kind of print the accuracy, so the accuracy now is going to be round. So we're going to round our log results to get our test accuracy. And let's actually do that to me. And 2. So we could just print that, it gives us 0.5. So yeah, that's it. So we could do for precision. What's the next one we're going to be looking for? F1. So these are actually the values. Now we can now perform a hyperparameter tuning in peace, and then we can now see grid is equals to GridSearchCV. And then we're going to pass in our hyper model, and then we'll pass in, we'll say param grid, param grid is equals to param grid, and then what else are we interested in? CV is equals to CV, and then we're gonna be scoring, maybe accuracy. So let's run that and see no issues. So to get our best estimator, I think we are good with this. We could just comment this out. So to get our best estimator, our best parameters, We're gonna do grid dot fit will pass X train scaled and then Y train. So that should work without any issue. Of course, it has done that. And that is it. So to get our best parameters, we're going to print best params grid dot best params. So lib linear, so over 0.1 is the best, and max eta, we didn't add max iteration. So there are also other things we need to add because remember in the notes, we clearly mentioned that during your hyperparameter tuning, there are actually a lot of, tunes that you need to add. And then I'm just going to show what I'm talking about. You need to actually add some features, but that's fine. We are very much good and okay. So we're going to say our best model is equals to grid dot best estimator. So this is our best model. So we're going to now say tuned y tuned pred is equals to best dot predict that should work. And then our y-tuned prober should be best model dot predict prober x test scaled up to 1. And then we can now print our final accuracy, which is what we're going to be printing right now. So how do we actually print that? So we're going to now print tuned accuracy is now going to be accuracy score. Then we'll pass in our Y test and our Y tuned pred. That gives us some kind of 51%. Then there's actually a lot to be done in this model. So can I just print other metrics like maybe precision, and it's going to give some kind of precision score. Then we have our Y test and our Y tuned pred. So that's actually a lot of things is that it's definitely going to give you, and so that is that. So that's basically how we perform our hyperparameter tuning. Basically, I've seen the model, but it doesn't really uh, show that, you know, yeah, it's basically a demonstrate everything that we really need to know, and it doesn't really show that we're wrong, we're clearly correct. And this is very outstanding and very nice. There's kind of an improvement from 0.50 and all of that. So we just tuned our hyperparameter, guys, and I think I'm just going to drop out with other. We're going to also add up other metrics so that so it could just make some more sense, for us. And yeah, of course, we could just like have very massive fun in making our predictions. All right, so actually, these are what I just wanted to do. I just kind of wanted to point out some things. And yeah, so what might I want to print? Maybe I could just print confusion matrix. Let's see if there's kind of, let's see the last improvement there. And then we have confusion matrix that will pass in our Y test and our Y tuned spread. Okay, so we'll print our classification report too, and then we can have classification report, our Y test and our Y tuned, spread. All right, so that is that. And what else can do I want to print out? Oh, confusion report all trashed out. Unless I'm going to kind of print our new ROC, our new ROC score. That's going to be ROC, AUC. This is now going to be Y tuned proper. Oh, what's that? Invalid. Okay, I have what's the issue? What was the issue? Okay, this is supposed to be inside. And that is it, guys. Okay, whitened is not defined. It is, please. This is it. Whitened proper. You know, guys, most times, you have to see your cell not kind of running. So, guys, what about if we kind of plot our whiten, our ROC together? And what do you guys think we're gonna have? So let's just try it out. So we can do that. So we could say our new FPR, our new CPR underscore is going to be equal to ROC curve, and then we'll have our Y, of course, our Y test, and our Y tuned rubber. So what can we do with our plot dot figure fixed size of 6 and 8? Plot dot plot, and we have FPR, remember before, TPR before, label, then is equal to F string, so I have an F string of ROC, and what I'm going to call this, I'm going to say before tuned ROC. I'm going to go, let's shorten it, let's call it old ROC AUC is equal to ROC score. And dot 2F to do this math. Then we could say plot dot plot. And then we can have new FPR, new TPR. Then we're gonna have a label is equals to F string of tuned ROC. It's gonna be equal to, I think it's good to add that equal to sign there, and we have ROC AUC score, and then we'll pass in our Y test, and our Y tuned rubber. Okay. Dot 2 dot F to F. This is supposed to be a dictionary. I think that works. No, this is not supposed to be a dictionary. It's supposed to be. I guess that is correct now. Okay, this is not supposed to enter here. It's supposed to stay outside. So yeah, plot that plot, and then I'm gonna put 0, 1, 0, 1, and then I'm gonna say line style is equals to this, and then also plot dot x label. I'm going to false positive rate. So this is the last thing I'm going to do. Plot dot y label. I'm going to call that true positive rate, and then plot dot x lim. Plot dot legend. Plot dot grid true alpha is equals to 0.5. We could just keep that 0.4, and the plot dot show. Also add plot dot height layout. And so that's basically that. Is there any other thing we can run this? What error? It's expecting too many values. Okay. And then we're gonna have an underscore here. That should work. Wait, what is the issue? There's still an error there. So 0 is not defined. Where do we have 0? Okay, that's here. So guys, you can actually see what our plot looks like, and it doesn't really show any kind of significant improvement on this model, but probably that is what the data set provides. We might want to just do some small touch on that data set, maybe on our trend test split, where we split it. We can say maybe stratify is equal to y. Let's see. But so just basically, this is just what we have, and looking for that. So we're gonna pass stratify equals to y, and then we run or. Hmm. All right, so that is that beautifully well. That is hyperparameter tuning. And then this is, okay, I didn't add a title. Oh, I forgot that. I should have added a lot title. So I'm going to call this hyperpara ROC curve for lung cancer prediction. after hyperparameter tuning. So that is definitely what that is. And I could just save it. So guys, of course, as usual, this code is going to be committed on my Git repository. And I want to kind of say very big thank you to each and every one of you for joining this session. That is quite of a pleasure because it shows that you really, really understand, you know, but more basically, why you're giving into this particular session. And that is that. So my next video, I'm definitely going to be doing some other things, but up to that, thank you very much for your time. I'm just going to do something lastly right now to commit it on my Git repository. So some of you might actually understand how to commit your terminals, how to use particular terminals during your Git commit, and version control is also a very important part of what we do, and quite very important, very imperative something. And something I say Git in it. First of all, I'm going to make sure I'm saving this Git in it. All right, so I'm going to say git add git commit and first commit. Okay, so it has those saved. I'm going to come here to click here, and then I'm going to say uh, ML. So I'm going to say hyperparameter tuning explained. Yeah, so I not really stubborn bugs ran into this video, just that we had some kind of crashes during, my VS Code stopped popping up, but everything is all right. Nothing to stress. And I'm just going to push that. I'm going to push origin. That should automatically commit my code to my Git. Of course, yeah, that commits it, and that is that for this particular lecture. And if you really found this video very insightful, please do share and keep in touch with me and all of that. So other than that, thank you very much for this session and being here. See you next time. Bye-bye.